I hope you are fine and you are doing well in your organic chemistry classes. Today we are going to discuss Diel order reaction, which is continuation of pericyclic reaction. It's one of the most important reaction in organic synthesis. Basically, it's a type of 4+2 cyclo-addition reaction. Why we call it 4+2 cyclo-addition reaction? Because it involves two substrates. One is known as diene, which contain two double bonds. They are conjugated, and another substrate is known as dienophile. So dienophile has only two carbon atoms, two active carbon atoms which are involved in bonding, and as far as the diene is concerned, there are two carbon atoms which are involved in bonding. So here we have written some theory with respect to a Diel order reaction. The reaction was discovered by two German scientists, Alder and Alder in 1928. They got a Nobel Prize in 1950 for their chemical work on this reaction during organic synthesis. It's a type of pericyclic reaction or 4+2 cyclo-addition reaction. When we talk about pericyclic reaction, basically pericyclic reaction involves the concerted shifting of an electron through a cyclic transition state. So pericyclic reaction are those reactions in which heat is required. In other words, the substrates are made to react with the help of heating. When you heat substrate, it undergoes a cyclization type of reaction and gives rise to formation of a product. So Diel order reaction is also a type of cyclization reaction which involves a diene and dienophile. So these two are the two important substrates. One is diene and another is dienophile. The dienophile is basically a nucleophilic character, and as far as the dienophile is concerned, it is electrophilic character. This is a nucleophilic character and this is an electrophilic character. In other words, we can say that Diel order reaction is a type of nucleophilic and electrophilic type of reaction. So when both substrates are heated, it gives us formation of product. But the mechanism is quite simple. We proceed through a cyclic transition state. Here I have shown the movement of a pi electron, which move in a cyclic fashion, gives rise to formation of a cyclic transition state, where I have shown with the help of a dotted line. This transition state ultimately transform into a product. What is important with respect to Diel order reaction is the presence of group on diene and dienophile. If an electron withdrawing group is present on diene, then it will reduce its reactivity. Basically, these group or the presence of this group doesn't influence the mechanism of a reaction, but it greatly influences the rate of a reaction. If we have a desired group on desired substrate, then it will accelerate the rate of a reaction. For example, when we talk of dienophile, then it is electrophilic in character. So whenever there is the presence of a such group which has electron withdrawing facility, then it will improve its reactivity. Or why? Because dienophile is electron deficient species. So a group which is electron withdrawing in character, definitely it will increase its electron withdrawing or deficient character, thus improve its reactivity. If electron withdrawing group on diene, if there is the presence of electron withdrawing group on diene, it will improve its nucleophilic character. Similarly, if there is electron withdrawing group of dienophile, then it will improve its electrophilic character. I have shown two examples. Electron releasing group such as methyl, which enhance the electronic density of the system through hyperconjugation, is more reactive as compared to simple diene. Similarly, here a dienophile has an electron withdrawing group, which is more reactive than a group which increase electron density of the system. So basically, this is a simple demonstration of the order reaction. As far as its stereochemistry is concerned, so basically when we talk of stereochemistry, either it can be retained or lifted during different organic reaction. But as far as the Diel order reaction is concerned, the stereochemistry is preserved. In other words, we can say that whatever the starting stereochemistry of diene or dienophile, they will be preserved in the end product. Just an example, here we have taken a dienophile with both the electron withdrawing group on the same side. So when a cyclization takes place in the presence of heat, it gives a formation of a product in which both the electron withdrawing group or substituent are either on the opposite side or on the plane or above the plane, or they are below the plane. But if we rotate the dienophile by making one group opposite to the other group, then its configuration will be changed in the product. One group will be above the plane and another group will be below the plane. Similarly, if we focus on the stereochemistry of diene, then we can categorize both the group attached to the terminal carbon atom of the double bond as a right group and a left group. If just for example take, let's we call it a group which is present at the left side of the double bond, and this is on the right, this is on the right, and this is on the left. So here in case of these ties, both the methyl group are on the left side. So in the product, both the group will remain either on the opposite side or below the plane of the product. Unlike these conformation in which one of the methyl group is on the right and another is on the left. So its product will be different stereochemically with one methyl group below the plane and another group upon the plane.